Oh, my phones are going. They're open now, really? Oh, yes, yeah.
Okay. How's everyone going? Really, that good? Calm down. How was your weekend? Learn anything fun?
That's hard, it's fascinating.
Learn that this class is hard? And you didn't know that already?
I had to guess.
What's my reputation? That I'm an easy teacher or a hard teacher?
Material hard.
Material's hard, I'm not. I'm a pushover?
No, you know,
Gee. You know a what?
you know what we try, I guess. I don't.
Okay. I talked to Trinity on, what was it, Friday?
Oh,
And I realized that I didn't put up the lecture, but then I realized the lectures are already all up. So what I'm gonna do is during office hours, I'll just do 30-minute segments of whatever we're missing. So for folks who want to come during office hours, I'll just try and do, like, we'll take a 15-minute break at the end of this class, then I'll come right back in here. We'll just
Okay.
do 30 more minutes. If people want to, but otherwise that way it's still recorded. It's on the screen. I can like work it out for anyone who's here. Because if there's not the talking back and forth, I feel like I'm gonna go too fast and not like see if anyone understands it. But that way we're at least at the right place by the end of this week. What were we talking about here? What is this thing? All right, let's talk about it. So you have some parcel of fluid that starts down here at Z naught. And we're going to move it isentropically. What does the word isentropic mean? Break it apart. Isa? Nope. Same. So same.
Oh.
Entropic? Yep. Of or having to do with entropy. Okay. So what's an isentropic process? No change in heat and not necessarily no change in energy. There's no change in heat, right? Because the addition of heat or the subtraction of heat, those are irreversible processes. So if I have something like an adiabatic process, what does that mean?
That your volume changes so that it allows that process to happen.
Yeah, an adiabatic change has no change in heat, no DQ, right? So temperature changes are due only to pressure work change, right? Or sorry, pressure volume changes. Okay, so isentropic means that you have a gas or a fluid that is both adiabatic and lacks friction. Isentropic processes are necessarily reversible, right? So for example, I start a fluid down here at Z naught, and I can raise it isentropically to here, to C, right? And then if I wanted to, I could play time backwards, and it would be just as realistic for it to go down, because the process is reversible. Does that make sense? Okay. So let's start with this fluid, and this fluid can move from point Z naught up to Z, which is Z naught plus psi. And the question is, now, does this fluid, it did change a little bit its density, right, as it moved. But is its density lower than the background? That is everything that's around it, or higher? Let's do this one first. If when I take this parcel of gas and I raise it up, it's now denser than the surrounding gas, what happens? Yeah, well, not for us though. I mean, just think about the parcel. What is the parcel gonna do? What? Parcel is just like an imaginary blob of gas. It doesn't have a real surface, but we're imagining that it has a surface. Okay, so that would be thinking that it'll squeeze down and become like the rest of the air around it. And that would be fine if it was in equilibrium here. But here we're actually letting it move. So I moved it up here, and then I said compare its density to the surrounding density.
Go down a little bit.
Go down. What do you mean? The parcel will move?
I think so.
Right. The parcel will sink. Right? So in this case, the parcel sinks. Because it's more dense than the surrounding fluid. What about this one? Where the surrounding fluid is more dense than the parcel. Good. Any idea what that's called? Instead of sinking? What? What'd you say?
You said buoyant, but I was.
Buoyant is correct. That is a buoyant force.
Oops, it goes.
So the only reason why I really want to drive this home is sometimes we think in terms of like particles instead of particles per unit volume. And we can run into just a grammatical issue where we say, oh, this is heavier than the gas around it. Well, it's not really that it's heavier, right? It's denser. Because, for example, you can have light things on tops of heavy things, right? So let's take an example here. Here's my piece of chalk and I place it on the table. There is no buoyant force that then makes the chalk rise up, right? But if this were a gas or this were a fluid, and I put a buoyant object, something that has less density than the surrounding, there actually is a force that pushes it up, right?
Then you lost me then. If rho is density, how come that one is, you're saying rho sub D is greater than rho sub C?
Yeah, this one here. This is the background.
Oh, it's the background, okay. You mean like the surround?
Yeah,
Oh.
yeah. Yeah, sorry, background means surrounding.
I thought those were for the person.
Yeah, so this solid line is the parcel. And the dashed line is the surrounding.
Okay.
And it can be, these are just examples of what the surrounding might be. It might be that the entire surrounding is right here, right? Right on that line. And if they're equal, then what happens? Exactly, just stable, sits there, right? Okay, good. So we say that the vertical density profile is steeper. Okay, so let's see which one of these three lines is the steepest. D. And what happens when the D parcel, if the background of density looks like D, what happens to this parcel? It flows up, right? So that would be a situation where you have gas from the bottom bubbling up. What would that be? Give me an example of this. What? Yeah, bubbles are a great example, right? That's certainly a much less dense object inside of a more dense object because that density is water and air. But that's not necessarily isentropic, right? Because that's an idealized version, right? Because we have friction, and you can certainly tell which direction the bubbles are going, right? Okay, so in this particular circumstance, but like boiling could be a good one. You know, before the bubbles actually start rising, and you just have hot fluid moving, you have an example like that, right? So bubble, soda, boiling, those all look unstable, right? And what's an example of, oh shoot, that's the wrong one. This is supposed to be here. And what about when it's shallower? So it doesn't exactly have the opposite of these processes that we're thinking about here. In fact, this one you may not even have known, you've seen it so frequently. So I want you to now imagine that there is a giant, we're in an ocean of air, right? And I want you to imagine with me, look at the table, there's the book there, and there's maybe air. And it's nice and warm and moist. It has a lot of water in it. Okay. And as it moves, let's say it's moving, it runs into the edge of the book. Now the book is not permeable, so what does the air do? Goes over it, right? So it makes a journey up. Right? And now maybe these parcels, maybe it happens isentropically, right? And so they make this journey up, and now they have to compare themselves to the fluid around them. So let's imagine that they're heavier. They're all filled with water. Right? What do? They sink back down. Now, what can happen? Imagine you go back down. By the time you get here, now what if your density is lighter than the surrounding area? Hey, go back up. So you can get waves behind a physical object because they're bouncing back and forth, overshooting some stable equilibrium, right? And we can see this with our eyes because when we see these types of waves, you'll see a line of clouds, a line of clouds, a line of clouds, and then we breaks in between. Every time that it's too hot, there's no clouds. And then it's cold and there's clouds. Does that make sense? These are called gravity waves. Okay, oops, this is not plugged in, nor is it paying attention. Okay, let's wake up, wake up. Okay, oh, great. Let's see anything here. What do you mean? Like seeing them?
Yeah, I mean, you're talking.
No. These happen like right off the mountains behind us. So if you look up and you see, like, here's a mountain, like the ones that, no, here's us. And then here's the observatory. Okay, and you see on the top of the mountain, like a big mountain, like that, right? Big cloud. But then you see a little cloud, a little cloud, a little cloud, a little cloud. That's probably from this. Oops, I'm not doing it well, but every time that it brings this moist air back up, cools, and then sinks again. Right? As it sinks, it heats, cloud disappears.
That's called gravity.
Yeah, these are gravity. And there's many different types of gravity waves. And the reason they're called gravity waves instead of like what you think about with neutron stars, is these are waves that are created by just the static equilibrium force, right? So the idea that you have different densities and they're either going to push you up, make you buoyant, or make you sink, right? Okay. So I don't know if we assigned this yet. Let's probably put this week, maybe, I hope. 115. Yeah, 115 is. So maybe we'll do this, maybe we'll want, maybe you'll prove it. So the idea is let's imagine you take some little parcel and you have these forces that are in balance. One, which is gravity pulling you down, and the second, which is the buoyant force pushing you upwards, right? And if you're around other objects near you that have the same density, then those cancel out. And the real question is whether or not your densities are different, right? Because that'll lead to motion. And so one thing that they ask you to do is to write out an equation for something called eta, or psi, I should say. Let me just write it here on the side. So here's psi, d squared, oops, whatever, you trust that thing, dt squared. And this piece here, if you remember from the other picture, I'm just going to draw it again. We have a parcel up here that's at z equals z naught plus psi. So some little deviation, right? And this down here is z naught. And this is the path, right? So this is some perturbation. And this symbol is the same symbol as that symbol. Let me control. Okay. So the second derivative of that object's motion, what's the second derivative mean again? Curvature, good. And when we're thinking about the second derivative of the length with respect to time, we would call that good. So the acceleration of this little perturbation is going to be equal to minus g over rho at this time, this period right here, right? Times d rho a dz minus d rho dz, all times psi. What do I write? This one here. This is row up. See, this is at this point.
The next one, it's above.
Oh, no. That's A. What's that?
Yeah.
Yeah, this is the same symbol.
The.
Oh. So this is row A, right? And this is row naught. So like row at row Z naught, so like that. Okay. So this is an acceleration of the particle, and that is due only to the differences in pressure with respect to height. Sorry, not pressure, density. So when we think about these first derivatives, we talk about them in terms of like a slope. You can say, how are they changing with respect to height? So in this particular circumstance, how the density changes with respect to height gives rise to the motion of the blob. Is that fair? Okay. What order is that equation?
Yes, first order.
First order on the right side and on the left side? Good. Okay, the reason why we like to think about this is that the order of the equation, let's say we're talking about equations of motion, it tells you how many initial things you need in order to understand the motion. So if, for example, I tell you something like dx dt equals something, right? Like dx dt is what? How do I think of velocity? Velocity, very good. So this would be what order?
First.
Good. So this would lead to what kind of equations of motion for x? X would equal initial what? Good. So the initial velocity times time, right? And what else? The initial position, right? So notice what we have here. We have one initial condition per order of the derivative. Let's try this again. What about for this one? Yeah. So this is going to lead us to what?
We need an initial velocity.
Yeah, we'll need an initial velocity. Right?
Probably just
What?
the position.
The position, the initial position. Good.
Oh, 18.
1/2 AT, right? You've ever seen that before for equations of motion? So now how many initial conditions do I need? I need the x, that's the same one. And the very good. So knowing the order of the equation is not completely useless. Right? Because it's really telling us what we need to know in order to simulate it. Does that make sense? Okay, what do the solutions look like for the Brunt-Väisälä frequency? You don't know what the Brunt-Väisälä frequency is, but I'm going to tell you. It's n, because we literally don't have enough letters. So this leads to this coefficient here. We call this n squared. And that's the bad spelling. Don't blame me. I gotta fuck this up. Every one of these A's has 2 dots over it. So that's 6 total dots plus the extra dot for the I. Okay. So what is the Brunt-Väisälä frequency? That is a measure of the ability to propagate gravity waves. Okay. So this is talking about the stability of the fluid, whether it is stable to convection. So what does that mean? Stability to convection means that you have some parcel that's going up, right? And then it is at the new density at the location that it landed is greater than the surroundings, and so therefore it sinks. And as it sinks, it goes down. It sees the surroundings, and it's now heavy or it's now lighter, so it goes back up, right? That's your gravity wave. What happens when it's 0? It can't do that. And notice what we said about this. We said this is the acceleration of our little motion, right? So if the acceleration is equal to 0, that means Yeah, shit's moving, right? Not moving, right? Good. Acceleration is 0 means that if it was in motion, it's staying in motion, but otherwise not doing anything, right? Okay, and then the other one is the convection one. So if it gets to the top and it just keeps going, right? Does this make sense? Love it? No, you don't love it? I thought you said that. Okay, we'll do one more thing, which is called the adiabatic. Oh shit. Hold on. You need this one? Okay, we're going to talk about something called the adiabatic lapse rate. So no fluid dynamics class would be complete without tying it to one of your favorite fluids, which is the one you breathe. Oh, such a good fluid. So you have two of your favorite fluids, which is the air you breathe and the water you drink. And in particular, the adiabatic lapse rate just is a measure of the vertical differentiation of T. So what I mean by that is we can, of course, think about something called adult lambda or big boy lambda, right? So it's not this one. It's not this one. It's this one. Same letter, but just Greek. Okay. So we can talk about the vertical distribution of temperature, and it gets its own name. And we call it dT, dz. Okay. So sometimes you would call that the temperature gradient. When you're talking about the atmosphere, they call it the lapse rate. Now, that probably makes sense to someone who works in meteorology. I don't know why they call it that. Normally I have a cool, like, break the word down, make it make sense. We don't have that here. Okay, so someone chose that name and it stuck. I'll figure out why, maybe by your early board. But what you can see here, right, is this is height, and this is temperature. So how will lapse rate show up on this graph? What?
Like, what do you mean?
What? Tell you?
Does that have to do with the, like, the stability?
Yes, this will have to do with stability for sure. We think about, so this is the thing that I called the lapse rate. How does this quantity show up on this type of a graph? What is the dt? So dt over tz.
Oh, just slope over.
So slope, right? So as long as I plot the temperature down here and the height here, the slope is what's being plotted, right? If I'm thinking about the lapse rate. Okay, so let's take this first slope down here, right? So this one. Okay. So this here is, let's say, the lapse rate. Okay. And all of these, they have the same slope. Right? Even though they're set apart on the page at different levels, they're just for our eye. Okay. So if I'm as, if I have the same slope as this, am I stable, unstable, or neutral? And what does that mean for my fluid?
It's the same as neutral.
The same, it's neutral. So let's think about what that means over here. Okay, so this has something to do with the difference in the densities as a function of C. And what I haven't shown you here is that we are treating the densities like they're only functions of temperature, right? So we can, in our mind, we can make an assumption. Now, of course, this isn't generally true, but we're making an assumption for an atmosphere, okay? And so we can say, okay, well, what's the temperature differential compared to the background? Because if it's the same, then the fluid is stable. It's not moving up or anything, right? Okay. So now let's look at this one here. This is the next part of the graph. What's the slope this way? Greater or smaller than the background?
Greater.
What's that? What'd you say? Greater, yeah, more steep, right? Even negatively steep, perhaps. That's an inversion, right? So let's see what happens over here. Okay. So this background here is negative, and it's subtracting off a negative. So two negatives make a bigger negative, and the acceleration upwards becomes well, think about if I'm subtracting two minuses, that adds together to still be negative, right? So I started by going up, and it's very strongly corrected. Does that make sense? It's very stable.
So still mean it's like not moving?
Can usually mean the opposite, right? It can move down. Right? Only when it's neutrally stable does it. Stable just means it doesn't run away. So a parcel of gas that comes up here gets shot back down. And these things called inversions, you actually see a lot in your day-to-day. You may see something that looks like the smog is like really thick, low down, and then it looks like it stops. That's usually because of an inversion. It's trying to get up, but the adiabatic lapse rate is such that it's like held down, literally, right? As it tries to move up, it falls back down. It's heavier than the gas around it, it falls right down, right? So this shape here, this is an inversion in the temperature curve. And then as we get over it, this is also stable, right? But that's not as shallow as the background, or it's not as steep as, right? So this describes the rate of change of the temperature with height. We will probably come back to that, but this is more for understanding something called scale heights. This is the differential relationship between the pressure in an atmosphere and the temperature. Okay. So what you can do is you can take the hydrostatic distribution. How do I write that, by the way? Yeah, let's say I wanted to write something like how does the density change with height? dPdz. Oops, I need to get rid of this. Get rid of this. I'll write it right on here so everyone can see. Okay, so the hydrostatic distribution is d E dz. What's that equal to?
Density graphs.
Good, almost 95. There you go. Perfect. Density times gravity. Good. Now we can make some assumptions, right? What does the ideal gas law say about the density?
I think it says it's pressure over RT.
Correct. That's pressure over RT. Okay. So I can take the hydrostatic distribution here and the perfect gas law, and I can combine them. Right? And now I can get a differential relationship that's going to take the pressure and relate it to the pressure. Okay? So let's do that. Let's do dP dz equals P over RT. Am I missing anything? A G and a... Very good. Okay, so now for you, on your papers, take 2 minutes and find the solution for P. Using that one on the right. Whoa. So there's P on both sides, right?
Yeah.
P?
Well, can you? I substituted a P.
How'd you substitute P? You don't know P.
Oh, we have the equation where E is equal to, where rho is equal to P over RT. Could you rearrange them?
Yeah, but you did rearrange that. You use this to get into here to get this.
Oh, okay, gotcha.
Yeah, sorry, let me just follow those arrows down.
No.
So these added together give you. This. All right, what's the answer?
That like exponential.
Oh, wow. E, right? When you take the derivative and you get the thing back, it's E. Good. So let's look at this one here. You got P equals what?
Negative E. To the negative.
Negative what?
Negative E to the negative GZ over RT.
What do you think? Should we positive or negative? Are pressures positive or negative? Okay, so that's fine.
Where's your DC go?
What do you mean DC?
DC.
I integrated, I moved it over.
Oh, you're right. I'm sorry.
Okay, am I missing anything?
Plus E,
A what?
plus an initial pressure.
Good, and how would you write that? P naught, right? Because the exponential, of course, has no units. Very importantly. Exponential is like a sine or a cosine. So it needs a coefficient in order to have a meaningful unit. So do we like that? Is that pretty? Ah, don't say no.
Why did you multiply it?
Yeah.
That's a very good question. Why did I multiply instead of adding?
Oh, is it because when you did the E? That's right, okay. Figured there's, yeah.
Yeah, you can think of it because when you do the dz, right, in order to do this, you have one dp over p, and so you do the integral, you get ln on one side, and you get your constant z plus c, right? And of course, when you do that exponential to get p by itself, and you get z by itself, then that plus c becomes p naught. Now, another way you can do this is just by guessing, okay? So what I mean by that is you kind of look around and you get the vibe, right? So you say to yourself, P has units of pressure, and exponential has units of
Same with E has yours?
Yeah.
Does it?
correct, it has no units. Just like sine has no units, right? Because up here, GZ and RT, those units need to cancel. They need to have a dimensionless exponent, and the answer is dimensionless. It's just a number, right? E to the blank is just a number, nothing special. So if that's the case, and this has all of our letters tied up in it, where did the units come from? Because I got units on this side and no units on that side. Ah, I can't possibly add a C here, right? I mean, could. But you'd still need to do P naught in order for this to be a meaningful solution. You see that? Should I say it again or be below that? That's real physics. None of this mathematician do it right stuff. Kind of just look at it and you're like, seems right. Okay. Not that mathematicians are bad, it just takes longer. Okay, so we found an exponential, and now you have derived what's called the exponential scale height, because this thing, okay, G over RT, we actually call it H, And that's RT over G. So this can also be written as P naught E to the minus Z over H. And so this has a very intuitive definition. So you add together a bunch of stuff that really doesn't mean anything, RT over G, you're like, I don't really know what that is. But in fact, the meaning here is this Z over H, the H is a scale height. That is how high you have to go before your atmosphere pressure goes down by a factor of E. How much is E? What's that?
What is it?
How much is E? What does the number E mean?
It's exponential.
Sure, but what does the number E mean? Just like I could ask you, what's pi?
It's great.
Hold on, let's do this again. What's pi? 3.14, good. What's E?
I think it's 2.63.
2 is definitely right. What's the square root of 2?
2.7.
2.71.
1.8.
What's the square root of 2? 1 point.
That's 1.7.
1.4.
1.
1. Yeah, this isn't 7, sorry. Okay, so these are all rational numbers that you just need to know the ballpark of. Okay? This number is basically 3. This number is basically 3. This number is basically 1.5. Okay?
Wait, so you can say that again for the height, is how high you can go before the E changes?
No. Before the pressure goes down by a factor of E, and you're thinking in your head when you hear the letter E, you're thinking about 3. So let's imagine that the pressure at the surface is 1 bar. And we go up 5 kilometers. And that's a scale height. What's the current pressure?
Like 15 more.
Okay, you multiply there. Does the pressure increase as we go up? Decreases.
Do you divide
A half or
15-ish of what we want?
how do you get 15 there? Let's say that the scale height is 5 kilometers. You go up 5 kilometers. The pressure is now
Doing with the, what's the first thing?
we're just using the equation that you derived. Right? P equals P naught 1 ATM E to the minus Z over 5 kilometers. D is the altitude, so however tall you go. So if I go up 10 kilometers, what's the pressure? Let's do the first one. Z equals 0. E equals good. 1. Z equals 1 or 5. P equals,
2 or 3.
excuse me, I see an instinct to go up. Pressure is going down as you go up. Let's put the number 5 here. 5 divided by 5 is
Oh, what?
5 divided by 5 is 1. E to the minus 1 is 1 over E. Right? Okay, let's do Z equals 10. P of 10 is very good. 1 over E squared. Let's go. Okay, so let's convert these into numbies. Okay, that's about a third. That's about a ninth. This is the power of the exponent. At every E folding length, you multiply by another E. And those catch up quick, right? So by the time that you get up 5 scale heights, let's say you are 25 kilometers in the atmosphere, how much has the pressure gone down by? This one you need to calculate for.
So. I just did 1 over E to the 5th.
Correct.
Okay, it didn't give me a fraction, but it gave me 0.0067.
0.0067. So that sounds like 0.67%. Not even 1% by the time that you get 5 scale heights up. How high up do things fly?
30,000 feet.
30,000 feet. How many kilometers is that? That's rough, right? 30,000 feet, 3,000 feet is like a kilometer. So it's like 10 kilometers. Is that reasonable? So somewhere between 10 and 20 kilometers. It's pretty crazy, right? So the pressure's dropped a lot. Why do they like to fly that up? Why do planes like to fly so high up? 50,000 kilometers. Pressure so low, and that means
Oh, it'll be buoyant at that point.
no. It's not buoyant because plane's big. Plane's made of metal. But say it again.
So it's less friction, so it's more efficient to fly if that's it.
All right. So where is the air the densest? At the bottom. So that's where you spend a lot of gas, right? Going through a very thick fluid. By the time that you get up really high, it is true you need to have enough air to keep you aloft. But you don't want to have too much air that's pushing you back as you move, right? So that's why they get up to what's called cruising altitude, right? You're just like above where it's turbulent, you're above where you're getting a lot of drag, and you just. We'll learn a little bit about planes. Okay, questions about this before we move into dynamics? Now, I mean, we've kind of been like hinting at it, but now we're really going to jump into dynamics in a meaningful way. How did folks feel about the homework? Wow, okay, hater. All right, so I will expect you to learn tensors on your own. And I know that that's a fucked up thing to do, but I'm gonna do it because we don't have enough time. I think that you will enjoy learning the applications of them. And if you do find that you're really struggling when we get to tensors, we can have like a very specific set of office hours devoted to them. But I just don't want to waste what little time we have in class on those. Okay, so that's section 2, Cartesian tensors, and really that's thinking about how to do sort of matrix multiplication in a meaningful way. How we do vector geometry. So if you don't remember that, if it's not like the most important thing in your day-to-day, which is totally okay, just brush up on it. Because where we're headed, you will need to understand large collections of particles, and therefore, you know, when we think about the mathematics of fluids, we are thinking about something that was developed to talk not about a single object, but about groups of objects and the way that they interact with one another. And for that, tensors are wonderful. Tensors are they're ubiquitous in more advanced mathematics. So if you're thinking to yourself that you're going to go into solid state, you're thinking about you want to move into radiative transfer, if you want to go into black holes, all of these use tensors and more. If you really want to learn a lot about tensors, you can take math methods too. Sometimes taught by me. They're fun. They're just it's a lot in them. Questions, comments, concerns? Okay. Next, let's talk about kinematics. Can you see this okay? What is this? What? Yeah, what's on the right? What?
It's a doctor handwriting.
Doctor handwriting. So this says, but I am very stupid today, and I hate everyone and everything. You know who that's by? Newton. So everyone has bad days, and sometimes you write them down, and people hold on to them 400 years later. So you can have these so-called like fathers of modern science, these luminaries in their field, and they have bad days, right? It's okay. On the left-hand side, what's going to happen is we're going to watch someone in an anti-gravity chamber pour water. So it's basically one of those things where you float, and the water's going to flow next one. Because like, who doesn't like cool videos of cool shit, right?
One of the coolest things in the wind tunnel is to see water floating. Poured from a jug, it quickly breaks up into droplets, the same size as raindrops, from around 0.5 to 4 millimeters in diameter. And standing there, you can experience what it would be like to fall with raindrops. They have a low terminal velocity of just 25 kilometers per hour. That's what the wind speed was set to for this demonstration. And what you can see is that raindrops aren't shaped like cartoon raindrops. They are closer to spherical, but a bit flatter on the bottom where they encounter oncoming air. If a raindrop gets too big, it flattens out, caves in the middle, and briefly resembles a little parachute before breaking up into smaller droplets.
Isn't that sick? Okay, so that's just where we're headed. It's really sick. Everyone loves it. We talked about adiabatic lapse rate, quiet charismani. Let's talk about kinematics. Let's go. Okay, so we're going to start moving our fluids. And we're going to start with really simple fluids, but we need to understand a bunch of terms. And we have to be able to be a little flexible in thinking about how we watch fluids move. Okay, we're starting 2D. So for example, here is our little tube and the flow is going through. So the arrows, of course, are demonstrating the direction of the flow, but they are also going to tell us the relative speed. So if all the arrows are the same length, that means same speed, same magnitude. And if they change, different magnitudes. Which are the biggest? Which are the highest speeds? The longer ones are the highest, right? Just like we know from vector physics. And so here you could have something, right? A motion of the fluid where maybe you have fluid and it piles up and then it unpiles up, piles up and goes out, right? Maybe you have some flow and it's described by a shape. And that shape is unchanging as it moves through the pipe. At this point, we don't care about what causes the motion. We want a way to physically describe fluid flow. Self-consistent. We're gonna have to make rules, right? Sometimes, okay, you have something like this, and the curve, there's some curve to the pipe or some change in the pipe, and it causes the shape to change. Right? Maybe it accelerates the fluid. Okay? So kinematics just describes the motion. Okay, this is the same way that we might think about something like x equals x naught plus vt plus 1/2 at squared, right? This is not a description of the forces. This is only a description of how does the fluid. Okay, we'll do forces and we'll do the reasons for the motion shortly. Okay, so what does steady flow mean? Not accelerating? So this is an interesting one, right? Because we haven't really we're not describing anything about the fluid yet. Like we haven't described whether it's inviscid, like whether it has no viscosity. We haven't decided whether it's an adiabatic fluid, anything like that. And already I've sprung on you a definition that seems a little hard to grasp because we're not talking yet about acceleration. You know, we're thinking about things like I'm moving this from point A to point B, right? That would certainly be an acceleration. But we haven't really described how that might happen with fluid, right? So in fact, the easiest way to create a definition for the word steady is to say that the flow does not depend on time. Okay? So if I look at the flow at one point and I look at the flow at a later point, they're identical. Does that make sense? Okay. So then by definition, what would unsteady flow be? That which depends on time, right? And that way we can kind of avoid having to talk about accelerations yet, right? We're getting there and you'll see that, but we're going to start with an easier version. Is that okay?
Would you say A is steady, C is not?
Good question. Would I say A is steady? Well, I don't know. Right? Are you saying, is it steady throughout the whole pipe? Because these things, are they moving? Right? These are maybe overdensities. Are those overdensities sitting in place or are they moving to the right? I don't know from this one. What about this one? What? You do know. So this steady or unsteady? Steady. Right? Because each one of these is matching up. Right? So unless someone comes in here and sticks their finger, it's not gonna. Okay, what's this one? Everyone likes unsteady? What? Okay, here's where it gets confusing. Okay, this steady flow says I don't care about change with respect to time. This is a change with respect to close. Yeah, the path. So it's a change with respect to space. Right, but think about it this way, okay? Imagine that this is a pipe that flows into someone's home. It could constantly be flowing this way and never changing, even though there are changes within the flow. So there are accelerations present in the flow, but the flow isn't changing and therefore it is. Do you see the non-intuitiveness there? So it's not enough to simply say, oh, there's a change in the velocity, and so therefore there's an acceleration, and therefore it's unsteady. No, because we need to think about the whole flow as well. Okay, very sad. Break from Monday. Okay, this one. What?
630,
Why?
60.
It looks like C? Yeah, okay. Cool. That's a great example. Yeah. Let's think a little bit about symmetries. So is there symmetries in any of these? Are there symmetries in any of these images?
Top and bottom, they're like mirror.
Good. Yeah, so this one you can flip it like that, right? Good. Anything else? This one? Good. This one? Good. This one? Good. Okay. So that's what we call rotational symmetry around the center axis. Good. And what about this one? Is it okay? Let's flip it over.
Is it the opposite direction?
Go in the opposite direction. Yeah. Depends on what we're interacting with over here. Okay. Good. Okay. So let's talk about particle. Oh, see that. We need to think not just about an individual particle in the fluid, we want to think about the field itself. So we're going to create something called a field. Okay? Because this is a formalism that has specific rules and it describes everything together as opposed to saying, okay, here's the motion of a single object. Okay? So on the top here, we have a sphere or a cylinder, whatever you want to call it. And this is embedded in some fluid. And there's two different ways of looking at this. We could look at it from the perspective of a steady flow around this pipe, right? So this thing is going around, right? And if I look at this here, right, steady flow, not moving, right? What about if I'm from the perspective of the ball moving?
It's not, doesn't look the same.
Yeah, so here's a weird looking thing. If I look at a single particle, this little piece here, right? Let me go around this thing. And I'm in the perspective of the particle versus the perspective of some fixed point P. Okay, moving along with you. Here, the particle is steady. Okay, moving along with the flow, it doesn't notice anything. Here, it's unsteady. Okay. So Lagrangian motion, that's the first word we're going to learn today, follows the fluid. Eulerian motion describes the flow through a fixed point in space. They are related to each other, and we will transform between these two coordinate systems. Okay? So the difference between this one and this one has only to do with the coordinate system moving relative to one another. Okay. And you can just think about that like this. This isn't going to work perfectly because I don't have two right hands, but if I did, I would stack them on top of each other. Okay. And then I would move. Then you would just move one relative to the other. That is the transformation of Lagrangian to Eulerian. Eulerians are a fixed point. Lagrangians move with the flow. You see that? It's gonna make a lot more sense when we see it, like physically in the fluid, and we haven't even put any equations down, right? So I'm just trying to prime us for thinking in multiple reference frames. Okay? Is one better than the other? No. They're both useful. That's why they're both developed and they're both named after people. Generally speaking, we're going to use the letter U, and what does that mean? The energy is always E. If I can get away with it.
That's the direction. Or
Getting very close. The velocity. But it's a specific type of velocity. This is going to be our bulk velocity. So this is not the individual particles velocity, which act like a perturbation to the bulk velocity. This is how is the whole fluid parcel moving. And it's going to be really important here that we use the vector U. Okay? You'll see why. Yeah, because remember, we're thinking not just about the individual particles, so it means you might have some collection of little v's, and they're all pointing in different ways. And then you have U. And U is how the whole parcel is. And what we haven't even begun to discuss yet is what happens when you squish on the parcel. You might get little v's to go up without getting U to change. Right? Okay. Make sense? So you might write it like this, and of course you could be more specific. You would have A, that would be what? UDT or D, the RDT squared. Yeah, either one. I like both. Okay, so this will be the nomenclature we'll use for kinematics. Okay. Oops, let me delete this. Don't cry. I kind of just wrote that. Genius, ahead of the slides. Here's the particle. Starts here. And it has some distance, little r naught, and it happens at some time t naught, and then it follows some path. And it doesn't have to be straight, right? It just has to be a path. We don't care about how it got from point A to point B. In fact, it can do a little loop on itself and come back. Doesn't matter. Only thing I care about is the motion of the object. And in this case, the object will be like a parcel or a fluid group as opposed to an individual. Okay. We can take any fluid flow property, big F. We're going to just do this kind of generally first. Give me an example of a fluid's property. Flow property, anything? What? No, that would be the type of fluid, but like what's a property that a fluid might have? Density, good, okay, density, right? So let's say we want to track the density. Take any flow property, think in your head density, right? But it could be anything. Okay. So you can apply the chain rule. Okay. And what you'll find here, and this is going to be a little sticky to do in a minute, but you can say something like F of R, okay? And this is of T comma R naught T naught. Okay, that's like where it is along in the path, comma T. And I'm going to simplify a lot of this really quickly. I'm going to just call it X. Let's call this thing X just for one dimension, make it really nice and simple. So I might call this something like F of x comma t. How do the properties of the fluid change with respect to the distance and the time? And of course, the distance is tied to the time. So it's a little self-referential. Okay, so let's take a derivative. Okay, let's do d dt of f of x and t, right? Well, I just said that x has t in it, so I need to use the chain rule. Right, so the first piece here is d dr1 of f dr1 dt. Assuming there's 3 dimensions in every spatial vector, okay? Plus the other one, plus the other one. This is for 2, this is for 3, right? And what's the third one? Or sorry, what's the fourth one? I did the first spatial component with respect to t, the second spatial component with respect to t, the third spatial component with respect to t. What's the fourth one? What? Sorry, what's the last part you just said? T, the actual derivative with respect to t, right? Partial f. Oh fuck. Partial t, right? And that is called the total derivative. So this is a total derivative. Oh god. You pretend like I spelled that. Of the quantity f. Okay?
What is it next to R, like in the parentheses? The very first thing, not the very top. Yeah.
So this is r. Remember we said that r is a function of t, its starting position, and its starting time. So I've tried to write all of that right here. But I ran out of chalk space. Okay, so this is getting us somewhere really important because now we get to talk about the total derivative. Okay. Now we said in a fluid that we start off here and we go somewhere else, and there is this sort of like double dependence on time, right? Well, of course, I can write this as something else. What is dr1 dt? You won! Bada bing, bada boom, let's go! Okay, so this one will give me U1, this one will give me, and this one will give me, good. So let's rewrite this thing. Okay, how do I rewrite that? I'm gonna write that as d dx of f. What? I want to do all 3 particles. I want to do all 3 terms at once. A dot of. Yep. So this right here is our del, right? That's the gradient of f. But what if I do this? So this is a vector. Now the first part is going to be multiplied by u1. The second part is multiplied with u2, etc. Right? And this piece here, of course, I should write it more properly. Is not just dvr, but it's and that's the gradient of f dotted into the velocity. Okay. So this thing simplifies a lot. I'm going to write here, and we're going to make it more formal. We're going to write d dt. These are big now. F is defined as the gradient of f dotted into u plus the time rate of change of f. And this has really, really straightforward interpretation. I know I'm running long here, but this is really important. Okay. What this says is how F changes, like densities, for example, is only due to two things. One, did the density change with time? And did the flow change the density? So we could take a property in this room like how many people there are. Okay, the first one would be, did people walk in and out? Good, that changes the number of people. The second,
How big are
sure, yeah, you can say that. You can also say, were people born or died? Right? F is changing in time and it's changing due to the motion. And that is the way that stuff changes in the fluid. Okay. Okay, yeah. Yeah, we're just any generalized property right now. And we can go on and we can define it in specific terms later on. Okay, so we're really getting started with kinematics here. I think if we don't lose this room, come back in like 10 minutes. And if you want to, and I'll just keep lecturing for a half hour and make up for that other 2 lectures. Otherwise, you can just watch it when I upload it later today. Because I'm just gonna pause the recording right now and just pick it right back up. Okay, so what we've defined is the total derivative.
I get into the lab, make sure for complication.
This thing here, this big D, is a unique value that describes both the motional changes and the temporal changes to the fluid. Okay? This basically breaks down any change in a property of the fluid into 2 terms. The advection of the fluid and the unsteadiness of the fluid. So let's recall what the word unsteady means.
You said it does.
It does depend on time. So if the fluid does not depend on time, what happens to the unsteady part of the total derivative?
Goes to 0.
Goes to 0. So we say that a fluid is steady because of what condition? No, we say that a fluid is steady because of what condition?
Oh, derivative is not. And
Yeah, so this thing here equals 0 is the definition of steady. So therefore, we call this the unsteady part of the total derivative. If it's 0, it's steady. But you call this term the unsteady part, right? You can call it the steady / unsteady part, but that's a lot of words. Okay. So that just leaves you with another word that we haven't defined yet, and that's called advection. That's different from convection, right? So what does it mean to advect?
Convectors.
What?
Convectors.
No. What's that? What?
I'm thinking like that.
Evacuate? Okay, these are all in the right place. Maybe we should do a little etymology on it. It's this word right here. Advection here means moving with flow. Do you think of an example where that might happen?
Boats.
Boats? Yeah, okay, not really a fluid property. Okay, what do you mean by that? I think you're still thinking about stuff moving in a fluid. I'm talking about properties of the fluid.
Oh, like the speed,
Sure. Is speed a property of the flow that's moving? Is gravity a property of the flow that's moving?
the density.
The density is a great example, right? You might have some flow, and over here it's overly dense, and over here it's underdense. And maybe this highly dense group is moving towards the undense group, right? We will see that velocity can be transported, but I don't think you're quite thinking of that yet, right? I'm thinking of a property of the fluid that's changing. So let's take an easier example. We love water, okay? Let's think about the ocean. The ocean does not have the same salt content, the salinity, everywhere. Some places is more salty, and some places is less salty. And that salinity has a gradient. So let's imagine you have a very salty area over here. Salt begins to move towards the places that it's less salty, right? That would be diffusion of salt. But you might also have flow that brings the salty water to the less salty water. That would be advection of salinity. Does that make sense? Okay, so here's the term. This is the advective term. What? F is some property, some undescribed properties of F. Okay, because this will apply to everything. The total derivative of F is due to the advection of F and the steadiness or lack thereof of F. Okay,
Which other things, what other properties?
what are some other properties?
Yeah.
What about pressure in the flow? What about the temperature in the flow? What about the internal energy in the flow? What about the viscosity in the flow? What about the surface tension in the flow? Right, these are all things. We just don't understand them yet, so I'm not using them, right? Just generally. Characteristics. Okay. Okay, so let's ask a question. I want to make sure we're not about to get that. So what properties of the flow, or what things about the flow will cause advection to stop?
Talk about velocity as a property.
You can talk about it as a property of the flow, yeah, but we haven't quite described what that means yet, so it's going to be a little weird. Yeah, it's not something that we have an intuition for yet, but we will absolutely get there, and then you'll be uncomfortable. Yeah, let's be a little bit more specific with our words. I do love where you're thinking, but what property isn't changing such that you would use the word stable? Because stable to me is not descriptive enough yet.
Density, pressure, and
So, okay, so let's say this differently. You're thinking in your head, let's think density. Okay, so how can I get advection to stop? You're thinking let's think just about density. You're saying there's no pressure in the fluid? There's always pressure in the fluid.
Like velocity or something, like uniform velocity or like no velocity.
Okay.
But I don't.
Okay, wait, I like that, right? Let's look at the advective term. What does the advective term say? How do I read this from left to right?
Del and function of dot U.
Good. Okay, so that's a pretty smart way to read it. How would you read it to your cousin or your mom or your grandmother?
Change with respect to time of all the dimensions.
Sorry, excuse me?
Change with respect to time.
Time. There is no time in here. Remember that the gradient always means
Oh, it's partials of time. Oh, partials of the R.
partials of r. The time comes in here, remember? the time we've absorbed into the flow direction. So to Metzley's point, what happens if the flow is not moving? Yeah, if U is 0, then obviously 0 times anything is going to be 0 and infection will cease. Good, so we found the first way to stop infection. Don't let the flow go. Okay, what's the second way to do it?
He, like, don't let the flow go, but that means just freezing it.
Well, I don't want to change the state. What do you mean by freezing it? If it's not if it's not a fluid anymore, then we can't use fluid dynamics, right?
Okay, yeah.
Yeah.
Just. Yeah, it would be.
That's that one is opposite but same magnitude. That's all the academics are adding.
Sure, yeah, let me just stand in front of you.
Okay.
I only care about making the advective part disappear. What? There's 3 knobs we can turn. Metzley turned the U equal to 0, that turned it to 0. Let's turn it back to a number. What are the other 2 knobs that I can turn to turn that to 0?
Products and be 0 based on direction.
That's correct. How do I do that? So this is U and this is del F. So what did you want?
They're perpendicular.
Perpendicular. So if the flow is going this way, but the gradient is that way, then what happens? It's 0. Okay, so misaligned. So if U and del F perp. Right? Good. What's the third way?
Del F just happens to be 0.
Good. Exactly right. So if del F equals 0, then it is also not an advective. Just out of curiosity, what does del F mean? Del F. F is the flow property. Yeah, we're gonna use slightly more specific language here because it's not just change, but what kind of change?
And E and M, wasn't that one like the curling?
Curling would be del cross. If you're in the right ballpark, I'm gonna show you where you're right. Mhm. But when we talk about change in F, what kind of changes? This term of or having to do with time, temporal. This term
Functional.
yeah, spatial. Spatial changes in F. So we gave this example of salinity. Let's say you have a pocket of very salty water over here and a pocket of not so salty water over here. That is a spatial difference. if in the whole thing, the salinity is the same everywhere, then there's no gradient of F. And therefore, there's no advection of F from one point to the other. C'est bon? We like? Make a lot of sense? Okay, we're gonna see these concepts a lot, so get used to that. We're also gonna see these words a lot. So they don't quite make sense now. In like 10 weeks, you'll be like, fucking. Okay. Let's talk about streamlines, streak lines, and paths. Delete this really quickly. So when we talk about how we draw flow or when we visualize flow, a lot of the way that we learned how to understand fluid dynamics is by setting up experiments. So we have these like tubes that you look at and you say, oh, there's some curve, right? Like, how the hell did they know that? Well, we would have to know that by maybe putting something in the fluid, like a tracer, and watching how it is distributed. To your point, maybe we put a little boat on the top and we watch how it physically moves, right? So there are different ways to describe how we present the fluid to one another. And they're not all the same. Okay? So the fluid looks differently depending on whether or not we're following a single parcel, whether we're following a background point that isn't moving with respect to the fluid, etc. Right? So a streamline is the one that you may be the most familiar with in your day-to-day life. So you may have seen these visualized on like a plane in a wind tunnel. Okay. These are defined as the tangent curve to the fluid velocity at all points instantaneously. So let's say we take a snapshot of the fluid and we describe the location of all of the velocity vectors. So here's my box, and here's a little sphere in the middle, and the flow is going around it, right? So there's a particle here that's moving to the right, particle here that's moving to the right, particle here that's moving to the right. And then this one's deflected, and this one's deflected, right? Streamlines essentially connect all of those. So every single particle, right, is defined as the tangent points to the curve. So tangent going like that, right? And imagining that I'm really good at draw them all. Okay. Is that the same as the path line? Well, in the example that I just drew, probably for a single particle, but not always. Because we can have unsteady flow, right? This is a snapshot. This is happening instantaneously in time. And the path line is not necessarily the case. The path line shows you where a single fluid parcel, like this little guy right here, where it is and where it will be. So this is the path that this parcel will take. It's going to go from here to here. That may be exactly where the streamline is, but not necessarily. Okay. Finally, a streak line is a fun one. It connects all the fluid particles that are going to pass through a single point. So take this point here. Give me all of the particles that are going to go through that point. Okay, so maybe it looks just like that. Okay. And currently that's pretty boring for this flow. Right? You're kind of like, I think those all sound the same fucking thing. Sound like, what are you even talking about? So let's give you some examples of when that is not the case. That's steady flow, you don't care. Here is unsteady flow. Okay. So here on the right-hand side, see if we can do this. Okay. This is just in 2D. Okay. The streamline, what was the streamline again? The instantaneous velocity of the whole flow. So we can imagine the flow is passing by. Okay, and this is the instantaneous velocity of all the particles. Okay, up and to the right. Is that the same as the path line? No. Because the path line says what? It says we're one particle at the origin. Let's say we select the streamline, the path line, and the streamline through the origin. And we're going to look at all the things that happen. So this particular particle, the one that started at the origin, it does have velocity in that direction. But as soon as you start the simulation, he's like, bye. And he heads up into the flow. Okay? Comes back down and comes back to where he started. Because this is unsteady flow, there are changes in the properties. Okay? And similarly, what's the streak line?
How many particles into the space?
It's all of the particles that will go through the origin.
So the pathline is the most minuscule one, and then the streamline is kind of the one.
Yeah, I mean it's hard because I don't want to call one more important than the other. The path line does focus the most on a single thing. Streak line is all the things that will go through the thing. So in one case, the path line thinks about a single particle on its whole spatial trajectory, but this one thinks about a single place and all of the things that will experience it. What?
All the things that I'll experience in.
Yeah, in that one place, as opposed to all of the places that this one guy goes. So the way you can think about it is, an island. Okay? So you might have your favorite Instagram or TikTok social media person who travels all over the world and comes to one island. And you're following all their journeys on Instagram. That's the pathway. Or you work at the island and you see all these influencers come in, only at that island.
I think it's a line though. I would imagine it'd be a point.
Well,
Come out.
so it's just, remember, the streak line is not the streak line for all of these points. The streak line is only for this point. This is a streamline only for this point. This is a path line only for this point, exactly at the origin. Because we can create all three of these for every location in space. So over here, right, in the streamline example, x, y, z, I can create a streamline here that's tangential to the velocity at each location along the path, right? And it's going to change. Similarly, let's say I'm here and I move up. Maybe the flow is not in that direction anymore, but that direction. You see? So the streamlines might be completely different when you space all of them out. But for today, we're just going to learn how to do them at a single point and how to translate between. That's shitty or you like it?
Just like if I looked at this, I wouldn't, am I supposed to be able to tell how many particles went through the origin based off that streak line? Like,
No, I can't count a straight line. Or I can't count a solid line.
so it's just like a.
No, it's just you're. I'm gonna give you a flow in the first or this is the third homework. I'm gonna give you a flow. And you are going to learn how to derive each of these three. So I'm going to prescribe a flow. And what that means is I'm going to give you how the motion looks in X and how the motion looks in Y. Right? And then you're going to go through and you're going to think at a single point, what are all of these? What is the tangent of the velocity? What are all the points that go through it? And what is the lifetime of one dude who goes through that? That makes sense. Okay. The reason we like this is because it helps us understand this. So as I mentioned before, everything we do in fluid dynamics comes from watching it actually happen. And you get to do really cool experiments. I have always wanted to build a wet lab here, a water lab, water table. I forget what it's called. But essentially what that means is that you would do the experiments in person. And those would include things like what you're about to see here. You're gonna have fluid. Okay, here's the pipe. And we're gonna watch individual particles. And we're gonna mark them by smoke. So we put a little bit of smoke, little straight smoke, and then watch it move. Or sometimes it's bubbles, right? As long as we can put the bubbles small enough that they don't move up, we're perfectly fine. Okay. And you'll see that it goes from being great maybe at the beginning and not so great later. But what this does allow us to do is it allows us to take, say, a block, and we can watch it, that one block, because we can play frame by frame, and then we can connect them all. And we watch the lifetime of one block. That's called the very good. And you can compare that, of course, to a single location on the screen. And that, see all of the things that go through that is called the, got it, right? Okay, let's do TV time with Krismani. We got 35 minutes. Okay, you're gonna want to watch the whole thing, but not with me, because I don't have that time for you right now.
Follows it. Small enough so that they follow the flow file. There are a number of visualization wires. Here, 2 mils. And put the wire in the water. Electrolysis forms extremely small hydrogen bubbles, which are swept off by the flow. Most of these bubbles are small enough so that they follow the flow quite accurately. A few large bubbles are also formed. We ignore them in observing the flow pattern. Here you see a probe with multiple thin fingers, which makes many fine lines. Another kind of probe is a single wire with sections insulated so that we see bands of bubbles coming off the probe. In order to interpret flow pictures, we need to be quite clear about 4 concepts. These relate the pictures to the kinematic description of the flow field. The first concept is the path line. A path line is the trajectory or path of a given fluid element. Here we mark a small element with bubbles so that we can follow its path. If we took a time exposure, we would make the entire path visible. Instead, we superpose a path line, and you can check for yourself that each of these squares follows it.
Top line, good. Everyone likes how not confusing. Okay. Next.
A streak line is a little different. It is the instantaneous locus or trace of all the fluid elements that pass through a given fixed point in space. If we run a short, uninsulated section of a bubble wire steadily, it shows us a streak line. In steady flow, each particle coming past the fixed point moves down the same path, and therefore the streak line is identical to the path line. We can check this by resuperposing the path line you saw earlier. Often it is useful to use multiple streak lines to observe a flow field. We can make them with the multiple finger wire you saw before. The third concept we need is the timeline. A timeline is defined as the instantaneous location of a line of fluid particles marked earlier at a prescribed. Here we apply the timeline technique to a steady flow past an airfoil.
Yeah, so, and he hasn't yet talked about streamlines, but so in unsteady flow, that's when the path lines and the streak lines diverge, right? So we won't use timelines, they're in the book, but we won't use them as much. I think they're not as important for what we're gonna do. You're welcome to watch the whole video and he'll talk about them more, but I'm gonna skip around a little bit.
Near the
Show you
angle
that.
which gives zero lift, the portion of the timeline passing above the airfoil rejoins the point above the airfoil. Its foil out and is everywhere tangent to the velocity vectors of the flow field.
The streamline.
The streamline is essentially a mathematical idea and is very useful in many fluid flow analyses. But there's no way to make a streamline directly visible. You've seen that in steady flow, the path line and the streak line are the same. And you might suspect that the streamlines would coincide with them also. This is in fact the case. Consider a particle moving along in steady flow. As you saw, each particle moves down the same path line, so that it's always moving down this path towards the particle ahead of it. This means it is always tangent to the path, and that is how we defined a streamline. So in steady flow, the streamline, the streak line, and the path line are all the same, and we can use either streak lines or path lines to show us the streamline pattern. Another thing we often need is the velocity vector field itself.
So let's do unsteady flow. Okay. This particle? What are they making right now?
Now compare the path line with a succession of instantaneous streak lines entering through the same point.
Okay, so that was the path line of one particle, right? Now watch how it happens when they pick a single point, you watch a bunch of things come. One. Ah, this is the location of
None of the instantaneous streak lines coincides with the path line. Here is a second element entering through the same point, but starting at a different time in the cycle of the plate. Notice that its path line crosses that of the first element almost at right angles, and it leaves around the other side of the plate.
A different particle, same location that it came out of.
Now you see elements marked at both times in the cycle of the plate.
Steady flow, the path lines are completely different. The streak line shows you all of the points that come out of this part and what they do.
If we superpose the path line of the second element and compare it with a set of streak lines through the same point, you can see that none of them coincide with the second path line either.
Right? Fluid hard. Okay. Okay. I've held
Now
you
let's
more than
see
you're
about the
supposed to, but I highly recommend this YouTube video. Flow visualization. It's like 35 minutes. If you just skip past the parts where it's an old man talking, you'll have a really good time. Questions, comments, concerns? Okay.